Welcome back to our second video for Notes 2.1, where we're still looking at the introduction to probability. So here on the screen, just a little reminder of where we left off. We were about to start talking about how to physically calculate a probability. So remember, P just stands for probability. Inside the parentheses is whatever outcomes or events you're looking for. We put the number of outcomes that are related to our event, in other words, what we want to happen, over the total possibilities, total sample space. So picking up with example 4, Beck is allergic to peanuts. At a large dinner party one evening, he notices that the cheesecake options on the dessert table contain the following flavors: 10 chocolate, 12 caramel, 12 peanut butter chocolate, and 8 strawberry. Assume the desserts are going to be served to the guest at random. So what we're looking at is what are the chances, what's the probability that Beck's cheesecake contains peanuts? We're looking for the probability that there are peanuts. Now, y'all, I'm not fixing to go perform an experiment here. I'm looking at my total options. This is a theoretical conversation. In theory, we should look at the number of options or outcomes that have peanuts out of the total options or outcomes. So peanut-wise, there are 12 peanut butter chocolate desserts. Looks like those are the only ones with peanuts. So there's 12 with peanuts out of my total. 10 plus 12 plus 12 plus 8. Total sample space here. If we add those up, we should get 42. Probabilities can be as a simplified fraction, a decimal, or a percent. If it doesn't specify, then you get to choose. So here we're going to practice all of them. 12 out of 42 could be simplified. Let's see what happens. Actually, I think I can take a 6. I could divide a 6 out of top and bottom. If you're not sure, simplify it by 2. Divide 2 out of top and bottom and see where you go. 12 divided by 6 is 2. 42 divided by 6 is 7. So simplified fraction. There are 2 out of every 7 outcomes that are peanuts. The other thing we could do is take 2 and divide it by 7 as a decimal. We would typically want to round that. So I could do it as, let's go 3 decimals, which would round out to be 0.2686. Or you could give it as a percentage, which would be 28.6%. Any of those would be accepted. Let's try another one. Same scenario, still Beck. We still have our total desserts to be 42. This time we're looking at the probability that Beck's dessert does not contain chocolate. So I'm looking for the probability of not chocolate. That is the number of options that are not chocolate over, again, my total options. So if I'm looking for not chocolate, caramel and strawberry are both considered not chocolate. So for not chocolate, let me write it here. I have 12 plus 8. There are 20 options out of my total. Whoops. So if I have 20 out of 42, if you're going to leave it as a fraction, you do need to reduce it. Let's see. I know I can at least take a 2 out of each of those because it's even, giving me 10 out of 21. And that looks to be as low as we can go. If you prefer the decimal version, 10 divided by 21, 3 decimal places would be 0.476. Or as a percentage, remember you can multiply by 100 to turn it into a percent, 47.6%. Almost half. 47.6% chance of not having chocolate. All right, let's try a few more. Example 4 was a little nicer to us because it went ahead and just listed out the options. Sometimes we will have to list out or find the options, our outcomes, for ourselves. So example 5 wants us to use that theoretical method to find the probability of getting exactly one boy when you have 3 children. If you are not given your sample space, you have to create it first. 3 children we looked at in our first video, and we found that there were 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So I'm going to go ahead and copy those down real quick. Whoops. All right, so there was my 1 boys, now 2 boys. Just playing with those orders. And then all boys. So you could have copied those straight down from our other example. Now, if I'm looking for the probability of 1 boy in the family, I have to look and see. There's 1 boy in the family. There's 1 boy in the family. There's 1 boy in the family. There were 3 ways of getting exactly 1 boy out of the total 1, 2, 3, 4, 5, 6, 7, 8 options. 3 out of 8. Now, let's have a quick little side conversation. Hint. If you don't want to have to list out all your possible options, all the sample space, you can use what I call the multiplication principle or the fundamental counting principle. What it says is that if I look at my options for the first kid, my options for the second kid, and my options for the third kid, remember the first one had 2 genders, second one had 2 genders, third one had 2 genders. 2 times 2 times 2, there will be 8 total outcomes. So that's a shortcut way that we will actually formalize more in the coming lessons. Now, this example also asks me to find the probability of getting a 5 when you roll a 6-sided die. If you have not dealt with dice very much, a 6-sided die is just a cube, so it has 6 faces on it. On each face, there's a number of dots. 1 dot, 2 dots, 3 dots, 4 dots, 5, and 6. So if I'm looking at the probability of rolling a 5, there is only one option that has the number 5 on it out of the 6. Hint, I could have asked you all kinds of things. I could have asked you to roll an even number. Well, then I would have 1, 2, 3 out of the 6. I could have asked you to roll more than a 2. So more than a 2 would have been 3, 4, 5, 6. There would have been 4 out of the 6 options. So we can ask you all kinds of different scenarios or events within one specific experiment. Let's go ahead and try one more. Example 6. There are 52 playing cards in a standard deck. There are 4 suits known as hearts, spades, diamonds, and clubs. Each suit has cards for the numbers 2 through 10, plus a jack, queen, king, and ace, for a total of 13 cards in each suit. Notice on there that the hearts are red, the diamonds are red, clubs and spades are black. So this is part of your formula sheets. You will be allowed a picture of cards on any exam in this class, because I know that many of us don't actually play cards much anymore. But cards allow for a really nice conversation and probability because it's a sample space we can look at. So if you draw one card at random from the deck, what's the probability of getting an ace? So the aces are the ones with the A on it. Jacks have a J, queens have a Q, kings have a K, aces have an A. So if I'm looking for the probability of getting an ace, that's just the number of aces out of the total cards. So looking, my aces are these A's, and there are 1, 2, 3, 4 of them out of the total 52 cards. Now cards can always be reduced, it seems, because I can divide a 4 out of top and bottom. 4 divided by 4 is 1. 52 divided by 4 is 13. 1 out of every 13 cards is an ace. So a few things for you to be aware of. These cards here that have a face on them can also be referred to as face cards. So if I ask you for the probability of face cards, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those out of the 52 cards. So we can play all kinds of these scenarios. One other conversation for us to have in this lesson is the probability that something does not occur. If the probability of an event occurring, it has the probability of E, then the probability that the event does not occur is 1 minus that probability. Remember, the probability of all your outcomes, the probability of your entire sample space is 1. Something in that sample space has to happen. So if you ever see this little note right there, it's called the complement. The complement of your event, aka the probability that it does not happen, is 1 minus the probability that it does. So example 7. The probability of a family of 3 children having one girl and 2 boys is 0.375. So the probability of 1 girl and 2 boys in the family is 0.375. What is the probability that the family does not have? So what's the probability of not having 1 girl and 2 boys? When you bring in that not, you're using the complement rule. The probability that it does not happen is 1 minus the probability that it does, that I do have my 1 girl and 2 boys. So 1 minus 0.375, which is 0.625. If they've already given me that probability, that's pretty nice. However, if they haven't, they would have had to give you some sort of information like Maybe you had to come up with a sample space. Maybe I have a deck of cards and I want to know what are the chances of not getting the number 2. Or they could give me a frequency table. This is our final example for this lesson. Find the probability of randomly selecting a social networking site user who is not 23 to 35. The probability of not being 23 to 35 is the same as 1 minus the probability of being 23 to 35. Well, this is one of those experimental probabilities. If I'm looking for the probability, so I have to have a side conversation with myself, of being 23 to 35, that's just the number in that category out of the total, aka my frequency over n. Those frequency distributions are not going away. So that age group saw 312 people out of the 975. So 1 minus my 312 out of 975 equals. Friends, all I need to do is take my total, 975, remove the 312, and that gives me everyone else. 663 out of that total, which can be given as a fraction or a decimal. So the probability of not being 23 to 35 is 0.68 or 68%. Is this the only way you could have done that? Well, no. If you remember when we did the not chocolates, we just added up everybody that wasn't chocolate. If I do not want to be 23 to 35, remove that category and add up everyone else. Notice I would have gotten the same thing had I done 156 plus 254 plus 195 plus 58. 663 out of my total. Now we're going to see the complement rule kind of be forced on us in some future lessons. But right now we're just trying to hit the highlights. Right now we're just trying to lay the foundation of understanding probability. So that wraps up this lesson. Practice, work on your homework, and reach out with your questions. In our next lesson, we'll talk about more probability.